So if we combine together the initial state, the actions function, and result function, together we define the state space graph, which is a graph where each vertex represents the state of the game, the edges are moves, and then a state can be reached by multiple paths. Now, we can superimpose a search tree over part of that graph to determine what move to make. We define the complete game tree as a search tree that follows every sequence of moves all the way until we reach a terminal state. Now, the game tree could be infinite if the state space itself is unbounded, or if the rules of the game allow for infinitely repeating positions. For example, this graph right here shows part of the game tree for a tic-tac-toe. So from the initial state with the empty board, Max has 9 possibilities for his action, right? He can take any one of these moves for Max, starting here. At that point, Min, depending on which action actually Max can take, has a number of possible moves he can make, and so on. So play alternates between Max placing an X and Min placing an O until we reach leaf nodes corresponding to a terminal state. This is a terminal state where Min wins, so the utility for Max is -1. This is a terminal state where there's a tie, so the utility function is 0, and this is a terminal state where Max wins along the diagonal, so he gets a utility value of +1. Now, for tic-tac-toe, the game tree is relatively small, right? It's 9 factorial, which turns out to be about 362,000 terminal nodes. So essentially, in a sense, we can do a complete tree search at each state to make sure that, to maximize the utility for either Max or Min. However, for chess, there are over 10 to the 40 possible nodes or states. So the game tree is theoretical, right? We can't actually replicate it and in the physical world and trace it like we can see with tic-tac-toe here. So what's the difference between games versus search problems? So in games, we have an unpredictable opponent. So the solution is a strategy specifying a move for every possible opponent reply. Okay, so if we look at tic-tac-toe, at every possible move that Min can take from the current state we're in, we're going to consider that in expanding the tree until we reach the final utility. There are time limits, so unlikely to find goal, we must approximate it. So unless it's a small game like tic-tac-toe, realistically we can't search the entire tree to find the best possible action at every state. So we have to use some way to approximate. So a perfect information deterministic game like chess, checker, or tic-tac-toe like we just saw. This is one type of game. That's what we're focused on. The other types of game easily have perfect information, but there is an element of uncertainty in it. Like Monopoly, for example, you use dice. Or You have imperfect information, but there's no randomness, it's deterministic like battleships, because in that case you don't really see what your opponent has, or imperfect information and randomness like poker or Scrabble. So let's look now at optimal decisions in games. How do we're focusing now on deterministic game with perfect information, so fully observable games. And let's see how we can use the min-max approach to find the optimal decision. So remember that max wants to find a sequence of actions leading to a win, but min, on the other hand, is trying to stop max from winning. So this means that max's strategy must be a conditional plan, okay, which specifies a response for every possible min's move. So in games that have a binary outcome like win or lose, we could use and or search to generate the conditional plan. So essentially defining a winning strategy in such a game is identical to the definition of a solution for a non-deterministic planning problem. In both cases, the outcome we're looking for must be guaranteed no matter what the other side does. Now, for games with multiple outcome scores, we need a slightly more general algorithm, which we call the min-max search. So if we look at this game right here, the possible moves for max at the root node are A1, A2, A3. Okay, so we're at the root of the tree, and max can do one of these three actions. Now, the replies of min are going to be called B1, B2, B3, and so on. Of course, here we call them A11, A12, A13, and so on. Now, this particular game ends after one move by max and by min. Okay, so the utilities of the terminal states range from 2 to 14. Okay, so you see that the lowest utility is 2 and the highest utility is 14. Now, given a game tree like this, the optimal strategy can be determined by working out the min-max value of each state in the tree, which is a function we wrote before as min-max of S. So the min-max value is the utility for max of being in that state, assuming that both players play to win, of course, until the end of the game. So min-max value of a terminal state is just its utility. So in a non-terminal state, max prefers to move to a state of maximum value when it is max's turn to move, and min prefers to move to a state with minimum value. So, in a sense, we can summarize this min-max at a given state. Okay, you pass in the state, the current state of the game, and to return an action, maximizing the min-max value. And then you have the function max value at a given state. If it's a terminal state, it's going to return the utility. But if it's not a terminal state, it's going to keep tracing all the way until it reaches a terminal state. And the min value is the opposite. Again, if it's a terminal state, it's going to return the utility. Otherwise, it's going to keep looping until it reaches a terminal state. So If we apply this to this game tree, the first min node has 3 successors. This is the first min node, has 3, 12, and 8. So its min-max value is 3. The other 2 min nodes have min-max values of 2. This one has a min-max value of 2, and this one has a min-max value of 2. So the root node is a max node. Its successor state have min-max values of 3, 2, and 2. So it has a min-max value of 3. We can also identify the min-max decision as the root. Take action A1. And the reason why we asked Max to take action A1 is because action A1 puts him on the path for the highest min-max value, which is 3 in that case, which is on this side of the tree. So the definition of optimal play for Max assumes that min also plays optimally, right? That min is doing his best to win as well. But what if min does not play optimally? Then Max will do at least as well as against an optimal player, possibly even better. However, that doesn't mean that it's always best to play the min-max optimal move when facing a sub-optimal opponent. So, for example, you can consider a situation where optimal play by both sides will lead to a draw, but there is one risky move for Max that leads to a state in which there are 10 possible responses by min that all seem reasonable, but 9 of them are a loss for min, and 1 is a loss for Max. So if Max believes that min does not have sufficient information to discover the optimal move, Max might want to try the risky move, on the grounds that he has a 9 out of 10 probability to win, right? Because we said only one case could lead to a loss in that case. So let's revisit our search algorithm.